So here is our polynomial again. I'm going to go ahead and one of the zeros that we found was c equals 3. So I'm going to divide 3 into our polynomial. And if you remember with synthetic division, you just write down the coefficients of each term across the top here. So I have 3, -7, 6, -28, and -24. And if you remember, first you bring down the 3, your leading coefficient. And then with synthetic division, you multiply diagonally. So 3 times 3 is 9. So I'm going to write that right here. And then we add -7 and 9. So you add vertically. -7 and 9 is going to give us 2. And then we multiply 2 times 3. So diagonally. And we're going to get 6. And then we add vertically. 6 plus 6 is 12. Then we multiply diagonally. 3 times 12 is 36. Then we add vertically to -28 plus 36 is going to give us 8. Then we multiply diagonally again. We have 8 times 3 is 24. And then we add vertically. -24 plus 24 is 0. And we know that that's the remainder when we're performing synthetic division. And since c of x has a degree of 4, when we divide x minus 3, our answer here is going to have a power of 3. So this is 3x cubed, okay? This is 2x squared. This is 12x, and that's just 8. So we can say here that c of x is equal to x minus 3 times 3x cubed plus 2x squared plus 12x plus 8. But we're not done. We want to reduce this all the way. Well, we found over here that c equals -2/3 is also a 0. So what we can do is continue our synthetic division. So all we have to do is just write this in here, and we're going to divide -2/3. That's the 0. I think just so that you can kind of see the powers getting reduced, I'm going to go ahead and kind of write these in here small. You don't have to do this, but I'm just kind of doing it just to explain what's going on here, but you're seeing it get reduced. Okay. All right. So let's go ahead and continue. So we're going to bring down 3. Then I multiply diagonally. 3 times negative 2/3 is negative 2. Okay. And then we add vertically. 2 plus negative 2 is 0. Then we multiply diagonally. 0 times negative 2/3 is 0. And then we add vertically. 12 plus 0 is 12. And then we multiply diagonally. Negative 2/3 times 12. Well, that should come out to negative 8 because we know that this is a 0. Our remainder should be 0. If you need to do some side work for this one, you can. I'll just do the side work here, but you've got negative 2/3 times 12, which we can write as 12 over 1. That's negative 24 over 3, which is negative 8. Okay, so that's a negative 8. We can go ahead and write that here. And then we add vertically. 8 plus negative 8. That gives us 0, which it should be because we know that negative 2/3 was a 0. So the remainder, which is what that is, should be 0. And that's applying the factor theorem there. And so now, notice since we started out with 3x cubed, so we have a degree 3 polynomial right here. Well, this is going to reduce down to a quadratic. We have x squared. So we have 3x squared. This is 0x and then 12. So now we can further reduce c of x. So c of x is now x minus 3 times x minus negative 2/3 times, we have 3x squared plus 12. Now, if you notice here, we have this 3x squared plus 12. There's actually a common factor here of 3, so we can go ahead and take that out. So this equals 3 times x minus 3 times x minus negative 2/3 times, if I factor out a 3 from 3x squared, I just get x squared. And if I factor out a 3 from 12, 12 divided by 3 is 4. Now, if I were factoring this just in the real numbers, I'd be done. But this x squared plus 4, this quadratic, we can actually factor this further into complex zeros. Well, to find those zeros, we can go ahead and just take x squared plus 4 and set it equal to 0. So we're going to subtract 4 from both sides. We get x squared equals negative 4. And then we're going to take the square root of both sides. So we get x equals, remember if you take the square root, that you need to do plus minus. So we have plus minus The square root of negative 4, we can actually split that into the square root of 4 times the square root of negative 1. And we just mentioned previously in the video that the square root of negative 1 is actually I. So this equals plus minus, square root of 4 is 2, square root of negative 1 is I. So those are the two zeros that you get from that. So then we can actually write that C of x is equal to 3 times x minus 3 times x minus negative 2/3 times, instead of x squared plus 4, we have x minus negative 2i times x minus 2i. We can go ahead and simplify this just a little bit. So this equals 3 times x minus 3 times x plus 2/3 times x plus 2i times x minus 2i. And so the task that we had was to solve the polynomial equation in the complex numbers. So let's go ahead and do that. So solving it isn't just factoring it, but it's identifying the zeros. So let's go ahead and write those down. So we have x equals, I'm going to go ahead and just write these in set notation. We have negative 2i. Okay. We have negative 2/3. We have 2i. And we have 3. So these are our complex zeros. Do notice that we have plus and minus 2i, and those come from the conjugate pair that we have here of x plus 2i and x minus 2i in the factors. We also have a positive real zero of 3 and one negative real zero of negative 2/3. So when we look back at Descartes' rule of signs, when we talked about the number of positive real zeros, it was 3 or 1. Well, we ended up with one positive real zero, and then instead of 3, those other two zeros ended up being the complex zeros with imaginary components of plus and minus 2i. And of course, we did have our one negative real zero of negative 2/3. And then right here, I just want to make sure that you see that this is written as a product of linear factors. And then this is just our expanded form where we started. So I really hope after this example that you understand a lot more about the complex conjugate pairs theorem, that, if you have real coefficients on your polynomial, if you end up with a complex zero with imaginary components, that its conjugate must also be present as a zero. Also, the fundamental theorem of algebra, that you're going to have at least one complex zero if the degree is of your polynomial is greater than or equal to 1. In this case, we had 4. And then the number of zeros theorem, that just tells us that every polynomial of degree n has n complex zeros, provided each zero of multiplicity is greater than 1 is counted accordingly. We didn't have any zeros of multiplicity greater than 1, right? These all had, when we broke them down to linear factors, they just had powers of 1. So they were all unique zeros. So with each of our zeros being unique and having a multiplicity of 1, then it makes sense that we have the 4 complex zeros, since this is a degree of 4. And then I also hope that you understand now after this a lot more about how we use Descartes' rule of signs to help us narrow down the number of possible real positive zeros and negative zeros, so that when you do use your rational zeros theorem, you don't have to try all possible rational zeros, because we could have a case like we had here where our constant term has several factors, like we have on 24. So then possibilities for p are really high. But like in our example, when we saw that there was one negative real zero, once we found negative 2/3 to be that one, then we didn't have to test out any more negatives. And that's using the remainder theorem, right? We use the remainder theorem and see if we get 0 as an answer. If we get 0 as an answer, then we can use the factor theorem to say, yes, that the factor associated with that 0 is a factor. So I hope you understand a little better how to use those two theorems to help you find the zeros and the factors. And then finally, how to use synthetic division to break down your polynomial to a lower power with a goal of getting it down to a quadratic where you can, solve it somehow. This one's a simple quadratic to solve, but if you needed to, you could use the quadratic formula and find your zeros and essentially write out your polynomial in fully factored form as a product of linear factors, which is what we have in this line right here. We were even able to break down x squared plus 4 as a complex factors here with imaginary components. Well, that's all I have for this topic. I will see you guys in the next video.